Hello guys, today we're going to be covering section 2.7, which is mean derivatives and rates of changes. Or rates of change, but whatever. So the first thing we need to worry about is the fact that, like what is the derivative, what are rates of change? How do we measure them? How do we try to find them out? But a lot of this just kind of builds up previously on what we've done with limits. So what we've done previously was the second function and used the properties of that function, assuming it's continuous, then we can, try to find its limit points if it's nice. So basically what the point was that we've done a lot more with limits now. So what we can do instead is now, instead of, focusing just limits of just, specific functions, now we can try to do something else. Let's try to work on that a bit more. So if you remember, what we did in section 2. Section 2.1, I think it was tangents. So let's just go over more about tangents real quick. So if you remember about tangents, like the construction that we had at the very end, the fact that we can use tangents to approach, we can use secant lines to approach the tangent line, then let's kind of use that. So just to review real quick of what that was like, we had, as Q approaches P, or, as X goes to A, and let me see if I can draw that. We have the secant line approaches the tangent line. And just to be clear of what that looks like, because what exactly is Q approaches P? So graphically, this will be talking about, let's say we have point A right here, we have an X, here another X, another X. And let's see if I can draw this one. Let's do this point. All right. So we'll call this point right here A. A. This curve will be f of x. So this point right here we'll call this point P, and this will be A f of A. And we call just an arbitrary point, on the graph, we'll call that point Q. And I'll be able to form, x f of x. So, again, kind of how does this correlate to the secant line or the tangent line? Remember that what we had was, whoops, wrong color. Was that this would be the tangent line. The line tried to basically keep what this function is doing at P. And then the secant line is going to be just one that goes through P and Q. And remember, if we moved, Q over to, this new x value, call this point now it's Q. And then what we got was that, it's a bad drawing, but whatever. What we got is our secant line began to approach, the tangent line. So basically, this allows us to, find out what the slope is, Now we have the notions of limits and continuity and all that. Now we can actually use the secant line, and we can actually use this information to actually find the limits now. Now we can actually try to find the slope. So remember the slope of the secant line. Remember we call that, let's see, we call that MPQ because it depends on 2 points. This was just equal to f of x minus f of a divided by x minus a. Remember, it's the same thing as just f of a minus f of x, over a minus x, but that doesn't matter so much. And then we had, and basically what this construction says, and this secant just means the secant line, was that as, as p, oop, backwards again. I always forget. In logic, we have p implies q, so, which is like, just basic stuff. Like if something is true, then it implies that. So p implies q. So always used to saying p implies q, not q goes to p. So as q goes to p, we have mpq goes to, m, where m is the slope of the tangent line. So again, we kind of don't really like that too much. We don't like to use that notation, but we can try to formalize it a bit more when we talk about specifically functions. So remember, we had this kind of intuitive idea. We've done this before, so let's actually now try to formalize it a bit. So let's actually do like a definition of a tangent line. So definition. The tangent line to the curve y equals f of x let's see, I remember we have to talk about a point P at the point. And that's going to be a f of a, just like above. Is the line through P, so it's remember a tangent line, we'll have to keep that same point. And remember the equation that we had for the slope was that m is equal to the limit as x goes to a of f of x minus f of a divided by x minus a. So, and just a quick reminder where that is that here, is the slope of the secant line, and then we have as q approaches p. That's another way of saying, as x goes to a, and then mpq would be this quotient right here. So that's where the limit would come in. But so this is our definition of the tangent line. So we have a tangent to the curve y equals f of x through a point P at a f of a is the line through P with, and then we have that slope, which is the limit of secants as the secants get closer and closer to the tangent. So, and I should also specify, provided the limit exists. And the reason why is that if you have if you have a function that is discontinuous or just some other issues where that limit might not exist, then you wouldn't really have a tangent line at that point. And if you want to try to, you can verify that on your own. Try to find a function where the difference quotient like that doesn't exist, but you'll have some issues trying to find the tangent. But let's do an example then. Let's try to find a tangent line then. So let's see, find an equation. Let's see, of the line tangent to y is equal to x squared at the point 2, 4. And that's just going to be 2 f of 2. Or, 2 of x squared, but that doesn't matter so much. The fact is, if you plug in 2 here, you get that point right there. So that's a good point. So now what? So here, if we kind of look at the definition, here we have a is equal to 2. We had our f of x is equal to x squared. So now we can actually use that. Now we can use the definition to find the slope. So we have that, m is equal to the limit as x goes to 2. We had f of x minus f of 2 divided by x minus 2. And that'll be equal to x squared, because f of x is equal to x squared, minus 4 divided by x minus 2. Oops, forgot the limit. X goes to 2. And that'll be, and the x squared minus 4, this will be like, x plus 2 times x minus 2, so x minus 2 will cancel, leaving you with just limit as x goes to 2 of x plus 2, and then, by continuity, that's just equal to 4. Alright, so that's a little messy. I apologize. Let me make it a bit. Oh, I got a phone call during the middle of that. Whatever. Alright. I'm not stopping. Alright, so the idea is, all you have to do is just appeal to the definition of, the tangent line. So the only thing we need is, a tangent line, we need a curve, we need a point, and then we can use that to find the limit. So once we've done that, now we found the slope. Now we can simply just use like point slope form. So it's like y minus y1 is equal to m times x minus x1. So y minus 4 is equal to 4 times x minus 2. And if you simplify that, you'll just get, y is equal to 4x minus 4. So that's our equation. So it's not too bad. The only real tricky part is just trying to find that slope. But you just have to understand that it's, as long as you understand, what's going on right here, and then being able to do the limit, then you're fine. All right, so again, so it's the tangent line. All right. So now there's a different equation or like expression that we commonly use to find slopes that is also like can be easier to work with in certain situations. So let's see. Let me just go ahead and say, this is gonna be like whoops, I did not mean to change that. I'll close that. All right, so I'm just gonna clarify. So there's another way we can do this. Oh, another expression to find the slope. I'll just put in quotations because it refers to the slope of the tangent line. But the idea is that, the idea of this, a new way to do it that might be easier to work with, the new expression is that here we have point A. So if we have a curve again, this will be like our point P, which will be like A f of A. And instead of just calling something X, we just say, we just move over. This is where you guys see that I hate these squiggles. We call this distance H. If you just move it over to the right H, then this point right here will be A plus H. And then if we move, to this point right here, what this point will be A plus H, then f of A plus H. And again, that could be like our Q. But now what we can do is, find the secant line going through them. It'll look like that. And we can kind of see as, as this gap right here, as, H goes to 0, then we have, like this, we have that, A plus H goes to A. So basically what this means is that, like, instead of just doing, A and X, and as X goes to like, A, we can do A and A plus H. So we don't need to say like an arbitrary point, we can just say a point that's like, H distance away. And I should clarify that this, just in case it wasn't clear, that this curve is f of x. So what we do is we let, in this case, if we talk about the last, if we talk about it in terms of like, what we did above, we'll say let x equal to a plus h. And then what we get is h is equal to x minus a. Oops. And then we have, as x goes to a, it's the same thing as h going to 0. And so what this gives us is an equivalent, an equivalent definition for the slope of the tangent line. So that's just a bunch of fancy words, but basically what this means is that this is basically, another way to set up a more useful, definition for the slope of the tangent line, and it may be useful in some settings, but it's not that it's more useful per se, but I like to use this one a bit more, but it's up to your preference. But what this ends up being is that here, if we had our slope m, remember that we previously defined it as the limit as x goes to a of f of x minus f of a divided by x minus a. But if we do the construction that we had right here, that if we let x equal a plus h, then what we get is the limit. And remember, we had as x goes to a, h goes to 0, so we can use h going to 0 instead. Then we have f of a plus h minus f of a. And on the bottom, we would actually have x plus h minus x. These x's would just cancel, so really it's just over h. And that's our other definition that we like to use. And you can, verify that it works, but it's the same thing. So if you try to do it, for this problem above, we still get the same solution. So these are two different ways we could find slopes of tangent lines. It's pretty nice, but, it's basically the same idea as before, but instead of plugging in x and a, we plug in just a plus h and a. All right, so now we need to talk about rates of changes, or rates of change. I say changes, I don't know why. But now, instead of, all the things that we said here, whenever we talked about, tangents, we talked about, instantaneous velocity, and also we talked about average velocity. So remember, just a quick review of what we had. Because every time we found, if you remember that we used our average velocities, which was the slope of the secant lines, and then we used them to try to guess what the slope of the tangent line was. And the slope of the tangent line in the velocity case is that the slope of the tangent line is equal to the instantaneous velocity. So this is going to be a lot of words, but I like to just use shorthand to kind of get the idea. So we say we have an object moving, and according to equation of motion, let's see, and what the S of t just means, S is the displacement, at time t. I should clarify or like specify a bit. It's distance from it, where s is the displacement of the object from the origin at time t. So what this means is, we have to specify like your starting location. Like when we talk about displacement, we talk about how far you've moved from one point to another. And when we say, or like s is the displacement of the object from the origin and at time t, what that means is that we just have a fixed starting location, for this function, which we just make it the origin, and then at each different time interval, that's going to give us your displacement at that time. So it's not too weird. It's still kind of like what we saw as above. But here we got to clarify, what is s really? So you say the function f of x. Well, the function f. Oh, wait, why don't you say f? Oh, I'm so stupid. All right, so this is s equals f of t. My bad. I made a mistake. Typically, some of the notation we might have, the reason why I made that mistake is that typically we can say s is equal to f of t, but this is, a lot of times you can just go straight to saying s is equal to s of t. That way, you don't really write this so much, but if you wanted to try to formalize it first, like what we're doing here, then we normally just say, s is equal to f of t, but really when we talk about these things, we'll say something like that. Let me say, oops. All right, so now that I can probably confuse you guys a little, but here we just say f, the function f of t is equal to or not equal to, but is the position function of the object. And what that means is that at any time of that function, it's basically going to describe the distance or the displacement of that object. Oops, I spelled object wrong. All right, object. Okay. So again, kind of what the graph could look like is here if we have this is s, if we have this is t, call this point A, call this point A plus h. And then let's do this pointer here and this pointer here. And this right here, this curve will be f of t, or, really s. Again, I'm just going to kind of stick with the notation that I used above the s of t. Sorry, whenever we go through these notes, you kind of want to try to generalize things as much as you can, but it's kind of weird when you try to generalize and also try to keep it consistent with what standard notation is. So try not to worry too much about how we define the curve specifically. Just know that our y value is equal to our displacement and our t is equal to our time. So this is why we typically just use this notation, so I'll be sticking with that. All right, so in this case, if we define this to be, s of t or, f of t, then likewise that we've done before is that this pointer here would be a f of a or a s of a. And this point right here will be a plus h, then s of a plus h. Or again, we just move an h distance away from a. So now let's actually try to use this to find the average velocity. So let's say a to a plus h, So that's going to be our time interval. Let's see. We have the change in position, which is, again, the change in position will be a change in y or change in s of t. Is going to be remember we have to start from the beginning time to the end time, so we go to a to a plus h. So that would be our final time or our final distance minus our initial distance, so which would be just f of a plus h minus f of a. Or let me keep it consistent with the notation. S of a plus h minus f of a. So, again, this might be confusing a bit. So let me just kind of clarify what we're doing right here is that we want to find the average velocity. But given this information, when we talk about average velocity, we need a time interval and we need a change in position, which is going to be this. So really, though, average velocity is going to equal to our displacement over time, or our, what I referred to as before as a change in x, or the change in y over the change in x. It doesn't matter so much what you want to call it. This is going to equal to, as you could say, f of a plus h minus f of a divided by h, or that's one way to say it if you want to keep the f notation. It's also equal to s of a plus h minus s of a. So what we get is that the average velocity, is the slope of the secant line PQ, where this was our P and this was our Q. So again, it's just, kind of just repeating what we've done before. But, the idea is, now that we've actually tried to formalize what tangent lines are, now we're going to have to try to formalize what instantaneous velocity is. So if you remember what we've done before, we had as time intervals get smaller and smaller, as time to time. Wow, I'm stupid. All right, my bad. I shouldn't call myself stupid either, because none of you guys are stupid. And okay, let's just try to keep it consistent. All right, so as the time intervals got shorter and shorter, I don't know. And what this equates to us is, as h goes to 0, because this is just another way of saying as t plus h minus t, because that's going to be the length of our time interval going to 0, but that's the same thing, it's just that. So as our, as the time got to 0, as the time got, closer and closer to each other, as the time interval got smaller and smaller, or shorter and shorter, whatever you want to say, remember we had the average velocity, and we had that approach the, actual velocity. All right, so basically what this is saying, oh, I should be careful. Yeah. So remember if we had that, so now we can define velocity in this kind of case. So now let's actually try to define velocity. So let's going to call that, or the instantaneous velocity. the same thing as just above. Oops. Let's say we call that, again, we need to call that like a function. We'll say v of a at time equals a. Oh yeah, I should clarify, this would be, if you want to keep that definition, if you want to call our velocity as like a function of v, then this would be, at v of a as well, or v of t. So then what we have as, so we define our velocity, v of a at time t equals to a, to be kind of like what we did before. We had said, like in terms of like the quotient, would be f of a plus h minus f of a divided by h, or keeping it consistent with what we said above, s of a plus h minus s of a. All right, so let me try to re-explain everything, or let me just go over everything again. So what we've done so far is just, kind of rehashed our understanding of, like tangent lines. I just gotta give you a review of it. Could have been a slightly better review because it's still early in the morning. But, we have the tangent line. The tangent line can be approximated, or, is the limit of secant lines. And we can define another way of doing that. We can do, instead of, a and x, we could do a and a plus h instead. And we just let the distance between a and a plus h go to 0, but this is the same thing as, like h goes to 0. So the way we can do that is, like, when we do that, we get basically like two equivalent definitions of the limit, or, the slope of the tangent line. And whenever we talk about that in terms of the velocity problem, like we did in 2.1, then, if we try to talk about velocity again, we need to say, like, a function s is, we have like an object moving, and it has, we can kind of track its distance, how far it's moved by some function. And then we get that function is going to measure its displacement at a certain time, and we call that function the position function. And again, where we can use, average velocity, we'll do an average velocity on some time interval of a to a plus h. And then we could use that to get a change in position, and then use that to calculate the average velocity. I mean, this is the same kind of stuff as above, as we've done before too. But now we're just kind of talking about it in a slightly different setting. And remember, like we said, the average velocity is equal to the slope of the secant line. At those 2 points. So whenever those 2 points got closer and closer together, which equates to us as the time interval is getting shorter and shorter, we have the average velocity goes to instantaneous velocity at that time. So that's how we define our velocity. We say velocity, which is, equal to like v of a. You could argue, like v of t, if you want to be general instead of, saying a. But we say the velocity v of a at time t equals to a is to be the v of a is equal to the limit as h goes to 0 as s of a plus h minus s of a divided by h. So remember, like, when I was looking through the notes of, like, what I kind of try to focus this on, they were using like two different kinds of notations. Either s is equal to like s of t, or it's equal to f of t, but basically the same thing. All the idea is that you're treating the displacement as a function. All right. So now let's actually try to talk about derivatives. So when you talked about tangent lines, what we talked about was we just said m. We just said the letter m. It didn't specify any functions or anything. But the velocity, when we say v of a, actually does kind of specify, maybe there's a function. Maybe we could kind of treat this nicer. But the first thing we need to do is, if we want to treat it more like a function, the first thing we need to do is define things at a point. So this is actually when we get our first notion of derivatives. So last definition. Now we get to the meat of math, or the meat of this course. You say the derivative of a function f at a, f at a number a Let me just underline that to kind of clarify what it is. Well, to kind of clarify that it's important. Derivative of function f at a number a. And don't worry about what that means just yet, or that might be confusing. So we denote that as f prime of a. And this means is like, and that notation means like a prime. So again, like this, let's just say this right here means like f prime, or let me say and that's just kind of like shorthand of how you would read that. You would say, that apostrophe, or I forgot what it's called honestly, but that just means like prime. We say that, we denote it as f prime of a, we say f prime of a kind of keeping with idea of like, before we said like the slopes of like, tangent lines. We have, f prime of a is equals to the limit as h goes to 0 of f of a plus h minus f of a divided by h, and this will be equal to, again, you can do the limit as x goes to a of f of x minus f of a divided by x minus a. So basically this is the same thing as when we talked about these tangent lines that we said like, m is equal to f prime of a. But again, that's basically where the idea is coming from. Is that we define the derivative to be like the derivative of function f at a number a, which we denote as f prime of a. We said, that's equal to like f prime of a is equal to like, the limit as h goes to 0 of f of a plus h minus f of a divided by h. So basically it's equal to the slope of the tangent line at the number a. Should note again that this only tells you at a specific point. Alright, sorry, I got confused because I was looking at my notes and I realized I made a mistake, but I just misspelled a word. Alright, so basically the idea is, kind of like with the slope of a tangent line only talks about a point. And so when we talk about the derivative function at a number a, again, this is only saying this is only at one point. So now let's do an example to find f prime of a. And also, in this example, I'm not going to specify what a is. I'm just going to keep it a. So I'm going to find f prime of a, if f, like, and with, I don't know. Usually I'll say like where f of x is equal to x to the negative 2. All right. So again, now we're just going to do it at an arbitrary point A, and we want to find the derivative of f of x at a point A. Well, that's a number A. So if you want to do, I'm going to use this notation right here, and you're welcome, we'll use, that definition right there, but you're also welcome to use this one as well. So we have the limit as x goes to a of f of x minus f of a divided by x minus a. And now let's actually plug it in. So we get 1 over x squared minus 1 over a squared. Oops, just got an email. Divided by x minus a. And now what we need to do is actually like simplify everything. You know, we got to keep on going, because if we just plug in a now, we just get 0 divided by 0. It is an indeterminate form. All right. So what I'm going to do here is, you know, find the common denominator. So this will just be like, let's see, a squared minus x squared over x squared a squared. Basically what I just did was, you know, let me just write it in blue. This was a squared over a squared. This is x squared over x squared, and then just move them together. But, you know, again, how you do this is not so important as long as what you're doing is algebraically valid. And what this bottom piece does right here, that'll just become 1 divided by x minus a. And you can double check that, but that's basically what will happen. So then let's begin to simplify now. So a squared minus x squared, that will be the negative. Whoops, I didn't even mean to type an s. But that will be like a plus x times a minus x divided by x squared. What the heck? Okay, that's weird. I didn't realize it was the thing. So again, that'll be divided by x squared, a squared, and then x minus a. But, you know, here we have these two terms which are pretty similar. So we can cancel them, or we can make one like the other. If we just put a negative right here, then what we'll do is, you know, not if we put a negative out there. But if we like multiply this thing by a negative, and if we like, you know, distribute this negative into here or there, or like take out a negative, it doesn't matter what you do in a step per se, but the idea is that whenever you cancel these, you'd get a negative remaining. And the only reason why is because you can only cancel them if you pull out a negative from one of them. But again, I wouldn't worry so much about that step. So then the last thing we have is the limit as x goes to a of negative a plus x divided by x squared a squared. And now we can plug in a, because this function right here is just like a polynomial divided by a polynomial. It's a rational function, so it's continuous, so that means that's just equal to, and basically what this means is we can just plug in a. Just get negative a plus a divided by a squared times a squared, which is equal to negative 2a divided by a to the fourth. Just get negative 2 divided by a cubed. All right, and let me just talk about the problem one more time. Was that here we wanted to find f prime of a. We just kept a general. We said f of x is equal to x of negative 2. I chose one of the two equivalent definitions that we used for the derivative, so I used this one right here. Just plug things in and just try to evaluate the limit from there. And so far that's it for the section, actually. It's not too much work. All right. Oh yeah, and one more thing before I finish. Let's see if I could. Nope, he doesn't want me to say. Nope, not what I wanted. All right, let me keep writing. All right, that's weird. Now, let me just try to finish what I was saying now, is that now that we have f of a, or, f prime of a, again, the derivative at a, we have the tangent line at our point P, which will be, a f of a, will have slope f prime of a. And you can double check that, but basically, the idea is that if we try to generalize the notion of tangent lines, if we try to keep that, if we decide we let our function m just to be kind of arbitrary now, then we can just use the fact that, our m now kind of becomes f prime of a. Because tangent lines are part of something bigger, but if we try to talk about them, in a bigger setting in terms of in a more specific setting of just terms of functions, then this is what we get. We get that, when we can define a line or like a function, if we can define a curve using a function, then we can talk about the tangent line in terms of its derivatives. And so basically this is the whole idea of, of like this chapter, and what we're going to be doing in the next chapter as well, is that, we take the notion of tangent lines and like secant lines, and we can take that behavior of what it's doing and basically use that to find, to call it something new. And whenever we talk about functions, we refer to them as derivatives. And they basically just have the same, kind of notation as prior. We still have the same behavior, have the same limits, and like so on. But they're pretty nice. But that's it for this section. Yeah, I think that's it. Oh yeah, don't forget to like, comment, and subscribe, I guess.